Welcome back to Electrochemical Engineering. Today I'm going to talk more about corrosion. Specifically, I'd like to talk a little bit about experimental measurements of corrosion. Last lecture we talked about Evans diagrams. And an Evans diagram typically has two curves on it. One curve representing the anodic process and one curve representing the cathodic process. We talked about how the corrosion potential and the corrosion current was where those two intersected. You could construct an Evans diagram by taking your working electrode, which is the piece under test that's undergoing corrosion. This is our metal of interest. Attach it with a typical reference electrode and counter electrode, inert counter electrode, using a potentiostat. And the rest potential, the potential where no net current is passing between the metal workpiece and the solution, is the corrosion potential. And when I mean no net current is passing, I mean the rate of anodic corrosion, oxidation, is balanced exactly by the rate of the cathodic process. Now, as we change that potential, if we make the potential of our working electrode a little more negative, we're going to start making hydrogen on that electrode, and the rate of the anodic process is going to go down. Alternatively, if we sweep the potential more positive, we're going to increase the rate of the anodic process, and the hydrogen evolution cathodic process rate will decrease. In those cases where we sweep the potential away from the steady state corrosion potential, the current passing on the working electrode does not need to be zero, because we can also pass current at the counter electrode. However, if we disconnect this wire, remember that the total current, the total Faradaic current happening at the corroding metal, must be equal to zero at steady state, because all the current has to flow somewhere. Okay, so let's walk through that. We can measure the corrosion potential, sometimes called E-corrosion. It's what's referred to as the natural potential of the system against the reference electrode. Its natural potential is set by the fact that it's simultaneously driving an anode and cathode reaction. And so that potential is going to be somewhere in between the equilibrium potential for hydrogen and the equilibrium potential, in this case, for iron dissolution. You can calculate the overpotential for either reaction from V core as the difference between those equilibrium potentials and the steady state V corrosion. The net current at the corrosion potential is, of course, zero. How do you measure this corrosion current at the corrosion potential if the net current is zero? Well, there's a couple ways to do that. One is to measure the weight loss of the sample. So you could imagine you had this iron sitting and getting corroded for some time, and you took it out of the solution and measured its weight every certain amount of time. But another way to do that is building off the voltammetry I just described here. You can vary the potential above and below the steady state corrosion potential and measure the current to make a polarization curve. Once we have this polarization curve with these two branches, we can extrapolate back to what the current would be for either the anode or cathode at the steady state corrosion potential. Remember, the cathodic and anodic currents cancel, so the net current's actually zero at this potential. But just like we do with a Tafel plot to find I naught, we can find I naught by extrapolating back to what the current would be at the equilibrium potential for one of the branches of the Butler-Volmer equation, for example. We can extrapolate back to the corrosion potential, which is not an equilibrium potential, it's a steady state potential set by the mixture of two separate kinetic processes. We can extrapolate back what the anode I corrosion would be under those conditions and how it would be balanced exactly by the hydrogen evolution current under those same conditions. So you can read straight off this prot a corrosion current of about 0.5 amps per meter squared. Now, you have to be careful because changing the potential from V corrosion may introduce other reactions. You'll want to understand your chemical system well and make sure you understand those. I also emphasize that V corrosion is not an equilibrium potential. It's not like U naught Fe2 plus Fe, for example, which is a defined thermodynamic quantity. V corrosion depends on the kinetics of the reaction. It's a steady state mixed potential. Now, if we assume Tafel kinetics for each single cathodic and anodic reaction, we can write something that sort of looks like the Butler-Volmer equation, but is not, is actually a corrosion equation that describes how the total current depends on the corrosion current at V corrosion and the deviation from V corrosion. So this has a form that's like the overpotential in Butler-Volmer, but note it's not the overpotential, it's the deviation from that mixed potential, that corrosion potential. And basically all this is saying that there's both a anodic branch and a cathodic branch, and the current increases exponentially in either direction as you move the potential away from the mixed potential V corrosion where the net current is zero. So that's the expression that actually describes the shape of this bolded curve here, this total current. You can see one branch dominates here, the other branch dominates here, and in the middle you need to think about both branches. The current is zero at V core, but we can get something that's analogous to I naught in Butler-Volmer, but of course it's not, because this is not equilibrium. This is I corrosion. It's the net corrosion current that's being driven by the forward chemical reaction. And this equation can be rewritten in terms of Tafel slopes here in the bottom. I'll also note that on the right side of this slide, I do have the Butler-Volmer equation, so you can see the similarity, but note I naught and I corrosion have very different physical meanings. One is related fundamentally to the kinetics of the reaction, the exchange current at equilibrium. The other is related to the rate of corrosion, which can be influenced by many different factors. We can define a linear polarization resistance. So if we take the equation for V core and we linearize it, that is, we just take the first derivative term, the Taylor expansion, we can define something called RP, the polarization resistance. So the polarization resistance can be defined in terms of the Tafel slopes, I corrosion, which is the current that's passing when the system is at the corrosion potential. It's the rate of corrosion at that mixed potential. You can see here as I core increases, the polarization resistance due to corrosion goes down. This is what you'd measure with impedance, for example. You could measure this polarization resistance directly, or you could do a very small sweep in a current voltage curve and get the slope to assess this polarization resistance. Now let's deal with mass transfer effects. Most corrosion rates are determined by Tafel kinetics, but something like the oxygen reduction reaction, if oxygen is oxidizing the metal, it can be limited by the mass transport of O2. Oxygen is not particularly soluble in water, so at high overpotentials you could actually run out of O2 to drive the corrosion process, and we need to think about that. Here's a plot of ORR current on the x-axis as a function of potential. And then what you can see is the ORR current is getting exponentially larger as we go to lower and lower potential, more negative potential. So this is on a log scale. So this linear part on a log scale, this is exponential Tafel behavior. But then at some point, at some current density, this plot begins to turn over and becomes flat. And no matter how much extra driving force you give the reaction, no matter how negative your electrode potential is, you can't pass any more current. So why is this? Well, of course, this is just the mass transfer limiting current. I mass transfer. Now, this limiting current, though, depends on the flow of the system. So here's an example of a so-called Reynolds number. Reynolds number is related to various parameters for our cell, including the flow velocity. So if we increase the flow velocity, we increase the mass transfer rate to the electrode, and we can get higher and higher limiting currents. So RE is the Reynolds number, and it predicts the transition from laminar to turbulent flow. So if you have a low Reynolds number, you get laminar flow, and if you have a high Reynolds number, you get turbulent flow often, and that's usually the case for a Reynolds number above 10 to the 5. I'll also mention that the oxygen reduction kinetics depend non-linearly on the concentration of oxygen. We'll come back to that in a moment. Let's consider a physical situation. Typically in electrochemistry, we like to think about the kinetic and mass transfer processes as happening in series. So we might have a resistor that we think about as being due to mass transport, and we might have another resistor that we think about being due to charge transport or kinetics. Now remember, at steady state, the current going through each of these resistors is the same. So the consumption of oxygen becomes a constant as you reach the mass transport limit. I might be applying more potential across this cell, across my equivalent circuit or across my electrochemical cell, but it doesn't increase the rate. So where is this potential used? How is it dropping across these various processes? One thing to remember is as you drive the reaction harder, you lower the surface concentration of oxygen in this case. Remember our very simple model from chapter 1, Bard and Faulkner. If we plot the concentration of, say, O2, we can have delta, and we're going to get closer and closer to zero here, concentration at the electrode surface, as we drive that overpotential more and more negative. Now, if you lower the surface concentration, this actually leads to a lowering of the exchange current density. The exchange current density is defined below here. You have some reference exchange current density defined for a reference concentration, usually 1 atmosphere of O2. But we need to account for the fact this reaction may no longer be occurring under standard state conditions. For example, if we are driving it very hard, we consume all the oxygen at the surface, so we can actually have an exchange current density here that is much lower than our reference exchange current density. Thus, the overpotential for both kinetics and mass transport typically increase when you're increasing the voltage or overpotential in the mass transport limiting regime. So let's look at that and think about how to read one of these graphs. This first curve here is depicting the polarization curve for oxygen reduction at the cathode. And what you see is you reach a limiting current at a little bit less than 5 times 10 to the negative 5 amps. Let's think about what's going on here. You have O2, and there's electrons getting pulled out of the metal to reduce the oxygen. And that's allowing at some other site metal ions to be formed, for example. So let's imagine the oxygen reduction reaction occurring with 2 different metals. So metal A, very strong driving force to corrode, very negative corrosion potential. You can see that if you extrapolate this curve back to equilibrium. Its equilibrium is going to be down here somewhere, very negative, very reactive metal. Metal B is less reactive. So we can figure out the corrosion potential as the point where these two intersect. And what you'll see here is the corrosion potential for metal B and for metal A are very different by almost half a volt. But the corrosion currents are not actually that different. And that's because you've reached the mass transfer limiting regime, where even if I put a more reactive metal in there, the reaction just can't go any faster because there's not enough oxygen to react. Now, you could have it go faster if you reacted with something else. For example, if we put the electrons on water to make hydrogen, for example. So we say the corrosion potential is then determined wholly by the potential of the cathode reaction. So it's clear that limiting currents and mass transfer play a significant role in corrosion when it's driven by O2 as the oxidant. Just to remind you, when migration can be ignored, so when there's either high salt concentrations, screen electric fields, or low fluxes of charged particles, the total flux, Ni, is just going to be given by a mass transfer coefficient times a change in concentration. And this is sort of a general way to write a transport equation. The challenge is understanding how to calculate this mass transfer coefficient. Notice this mass transfer coefficient has units that are actually similar to rate constants for electrochemical reactions. And so you can actually think about these in the same way. This is sort of a number that gives you an idea of how effective is the system at transferring mass. Now, that could be via diffusion, but it can also be via convective transfer. So often these mass transfer coefficients are described in so-called dimensionless groups. There's the Sherwood number, there's the Schmidt number, there's the Reynolds number, and the Sherwood number can be written as a function of the Reynolds and Schmidt numbers. And these are all sort of engineering numbers that you may need at some point. Here's the Sherwood number. It's related to the mass transfer coefficient by a characteristic length, for example, diameter if it's a pipe, or a length of a plate or a cylinder for laminar flow, and the diffusivity of the speed. The Reynolds number, which we introduced earlier, is related to the mass density of the fluid, the velocity of the fluid, again, the characteristic length, and the viscosity of the fluid. The Schmidt number is a ratio of the so-called kinematic viscosity to the diffusion coefficient. So all these have various uses in engineering, and we won't go through any of them in significant detail, but you may need to get out an engineering text if you need these in the future. So here's an example. The Sherwood number is typically related by a constant to the Reynolds number and the Schmidt number raised to some power a and b, where a and b are also constants. So we can plug this into our definition, our general definition for the mass transfer coefficient. And you can see that essentially you can get the flux as the Sherwood number times the diffusion coefficient over a length. And you can use this to define a limiting current density here, I limiting. And this value of I limiting can be useful if you can look up a Sherwood number or calculate it for a given system to get a sense of how fast can this electrochemical reaction go. How fast, for example, can oxygen get delivered to this surface? I'll just highlight a few other points here. There's something also called the Grashof number, which replaces the Reynolds number in other situations. Gas evolution can be quite important in some cases, and you might look at these equations and these sections in the book if you need those sorts of information. Now, so far, we've typically talked about a single cathodic reaction, for example, ORR, right? But you can also do HER or other cathodic reactions. So there's no reason why you couldn't simultaneously drive the hydrogen evolution reaction taking place at a low rate with the oxygen reduction being mass transfer limited. So you'd have to take into account the total current. This is the cathodic current. Is this just the sum of those two individual currents? I just note this here that you can't add logs like this, of course. These are not equal, but we can go and look at one of these plots here. And here again is potential. Here's the log of the current. Here's my cathodic branches, reaction 1, reaction 2, and this is the sum of both of them. And you can see this sum on a log scale here. And the crossing point now is determined by the total cathodic current, and where the total cathodic current curve crosses the anodic current curve, such that the total current is 0, and that gives us the corrosion potential, the steady state potential determined by the rates of both reactions and how they balance. I want to talk now about localized corrosion. Here's a picture of iron. You can see iron with all these pits in it. Very common when iron rusts, it starts to get these holes in it. And this happens when you have an anode region where the oxidation in the pit is separated from the cathode that's larger. So this is a case of localized corrosion, not uniform corrosion. I should point out that many of the equations we were talking about previously sort of assumed uniform corrosion. So why do you get this pitting? We introduced this a little bit at the beginning of this lectures. It happens because the anodic reaction takes place inside the pit, and it's the environment in the pit which keeps it from being passivated. And so I'll have you think about that in class. But notice here there's a passive film out here, and there's no passive film here. So if you think about what the balanced chemical reactions are for these different processes, and you think about the Poor-Bay diagram, potential pH diagram for iron, you might be able to predict why a passive film might form here and not there. So why corrosion would continue in the pit. even though there's a large area external to the pit over which it in principle could occur. Now, we can assume essentially a constant potential in the metal. Of course, it's not perfectly constant because there's some current flowing, but the difference in potential is very small, so we're going to take it to be a constant. But there is a significant potential drop in the solution from the anode to cathode. And this is what's driving the current. So if you think about this, right, we're driving oxygen reduction here. When we do oxygen reduction, we're consuming protons. So we're making hydroxide, for example. And when we dissolve iron, we're making iron 2+. So there's a driving force, right? To complete the circuit, we need to have positive cations move here outward and negative cations inward. Okay. And that's how we're going to complete our electrochemical circuit. So we need to have current being driven in the electron. Now, it's also interesting to note that the potential in the pit is higher than the potential of the surroundings. Of course, this makes sense. If this potential is higher than the outside potential, that's going to push positive charge out. So that's actually the migration needed to drive current through our electrochemical cell. So you could think about that as the solution resistance. And the potential across that solution resistor is driving positive current out of the pit because the pit is where the anodic corrosion is happening. And we'll just note that this is different from uniform corrosion where both reactions happen uniformly on the same location. So what are some causes of localized corrosion? Here's a picture of an extreme example of localized corrosion. You see this pit has etched holes in this entire iron structure. It can be due to grain boundary structure and composition. So grains are crystalline domains, and of course, metal is made up of many small crystalline domains. And the interface between two crystalline domains, some of those are going to be particularly susceptible to corrosion. And that spot is going to start corroding first, and then it will continue corroding via this process we've outlined here. Also, inclusions and defects can drive corrosion. Inclusions mean the addition, the unintentional, usually, addition of other materials in the metal. They get trapped, and this leads to defects and spots where corrosion can be accelerated. The dynamics of passive film formation and breakdown. Talk about the passive film. In this case, it's a iron hydroxide, oxide that can passivate corrosion in certain spots. And the local environment in the pit can be different. And we talked a little bit about this on the last slide, but you might be able to prevent this passivation layer from forming. So I'll have you talk about that in class, why the passivation layer might not form as readily inside the pit. And to do that, I'd like you to think about where the protons are made and consumed in this reaction, or hydroxides, and where are their pH gradients or not. So let's run through a few thought experiments about pitting, kind of a useful exercise to make sure we understand it. So one question you might ask is the potential measured inside the pit, i.e. with a very small reference electrode, greater or less than that measured with the same reference electrode outside the pit. So you could imagine if I had a little nano electrode or micro electrode, I could put a reference electrode in here. And I could put an identical reference electrode out here, right? And I could measure the voltage there. And I could ask, are those reference electrodes the same? And the answer is no. They're at different electrostatic potentials, and that will show up in the voltage you measure. So I'd like you to think about that a little bit in our in-class work today. But what you will measure is that the potential in the pit is actually higher. The reference potentials in the pit is higher that you measure with your voltmeter, and it's because of that electrostatic potential gradient. Now, you might say, okay, well, if this is a higher potential then, if phi1 is constant, then the place where you're going to have the largest driving force for oxidation is going to be actually inside the pit. So let's think about that in more detail. You can imagine I have my metal, has some electrochemical potential of electrons in it. That's this. And that electrochemical potential is the same here and here because it's all essentially in equilibrium because the current flowing through the metal is small and the metal is very conductive. Now, if the pit potential is higher in the pit, that's going to effectively make it so that electrons are going to want to flow more readily into solution, right? So a higher positive potential in the pit, which is driving the cations out, is going to lower the solution potential relative to the metal. So that's going to actually make reduction reactions more favorable. So what's interesting here is in the pit, the flow of current, this external potential gradient, actually makes it more likely to favor the cathodic reaction in the pit. But we just talked about how it's the anodic reaction that tends to happen in the pit. Why then does the cathodic reaction occur mostly outside the pit? Well, yes, the pit potential does favor the cathodic reaction by a little bit, depending on how much current is flowing. But very little O2 is really able to reach into that pit, especially when it gets deep, right? So you get a very large transport resistance to getting that oxygen in there. And the kinetics of the cathode reaction are slow, so the larger area of your overall metal surface is going to be better at driving that cathodic. Then, what keeps the corrosion in a pit active? Well, it's the same driving force that's inherent in driving the reaction, the difference between the equilibrium potentials of the anode and cathode. So the cathode would be oxygen, for example, and the anode the corrosion of in this case, iron. Let's shift gears and talk a little bit about galvanic corrosion. Galvanic corrosion is when two different metals are in contact and exposed to a common electrolyte. So we had this before. Maybe I have a piece of iron, right, and a piece of zinc in contact with each other. The metals corrode at different rates. Which one's more active, right? Which one has more active electrons? Well, we know zinc, if we put zinc in water or acid, it makes a lot of hydrogen. It is a strong reducing agent. Zinc is used in organic chemistry as a reducing agent. Iron is a much more stable metal. It's a weaker reducing agent. Now, the two metals are at the same electrochemical potential. And when this says equipotential, what it really means is U bar E of metal A equals mu bar E of metal B, right? These two metals, zinc might be A, iron might be B. The electrochemical potential of the electrons are really the same. Now, there could be an electrostatic potential across this junction, but remember, it's the electrochemical potential that drives reactions. Now, the cathodic rate is generally slower in these types of systems, and that's due to both the slow kinetics of oxygen reduction reaction. For example, it's a chemical reaction. It's typically going to have slower kinetics than metal dissolution, and the fact that you have O2 transport limitations. Now, the cathodic reaction in principle can happen on both metals, but it will happen faster on the less active metal. So ORR is going to tend to happen faster on the less active, more noble metal. And that's for a number of reasons. One of them is that this zinc surface is going to be corroding and oxidizing, whereas this iron surface will maintain some of its exposed metal to actually catalyze the ORR reaction. And as we said before, the potential drop in the metal is very small, so we can assume that these electrochemical potentials are almost equal to each other. So there's very little change in voltage, electrochemical potential of electrons through the metal, because it's close to equilibrium because the currents are small and metals are good conductors. But in the electrolyte, we could have actually a significant potential drop if we're passing significant current, because we're not necessarily operating in concentrated electrolytes. We might just have a little bit of water, it might be a very small concentration of salt, so you can actually get a fairly large ohmic drop in your electrolyte in these cases. Here's an example of zinc iron galvanic corrosion. So this figure here shows a cell, an insulator at the left, an insulator at the right, a piece of exposed iron 4 centimeters in length, and a piece of exposed zinc 1 centimeter in length. And what you can see here are the electric field lines in the electrolyte phase due to the current that's flowing, okay, between these two materials. We can write for the iron electrode the current in the y direction as the dissolution current of iron plus the reduction current of oxygen, reduction current of hydrogen. And all that is going to be a function of the potential in the electrolyte, where the electrolyte drop is occurring, because the potential in the electrolyte, remember, can affect the free energy remaining available to drive the kinetics of each of these reactions. So closer to the boundary, you'll have less potential drop in the electrolyte, and so the reaction will tend to be faster there. And the net current on the iron electrode has to be equal to the net current flowing in the electrolyte, which is just the conductivity of the electrolyte times the electric field in the electrolyte, which is the derivative of the potential with respect to distance. We can write the same thing for zinc with the same terms. Zinc can corrode, it can reduce oxygen, it can make hydrogen, and all these processes occur as a function of the electrolyte potential and the overpotential driving each one of these individual processes. And again, the current here has to balance with the current in the electrolyte. The current is zero at all other boundaries in this model. If you solve this, as is done in this plot, the closer spacing of contour lines, these are contour lines that show equipotential, so this is constant phi 2 here along these lines, just like elevation on a topographical map. The closer spacing of the contour lines indicates steeper gradients in potential and higher current densities. And in fact, the current density is highest where the metals meet. And so why is this? Well, it's exactly what we mentioned before. If you want to pass current from way over here all the way over here, you drop a lot of potential through the electrolyte. And if you drop a lot of potential through the electrolyte, you have less of the fundamental driving force, which is going to be given by the difference in the potentials for driving oxygen reduction versus driving zinc dissolution. That's a spontaneous reaction. But if you have to lose a lot of the free energy, use it up driving ion transport, you don't have as much to drive the kinetics of each of these reactions on each electron. So the current density is going to be highest right where these two electrodes meet. So let's think about this a little more. Let's look at the effect of solution conductivity on dissolution rates and locations. So this is the net current density now plotted from this model. And you can see that I can measure the dissolution current of zinc in higher conductivity electrolyte and the dissolution of zinc in lower conductivity electrolyte. And as you expect, in lower conductivity electrolyte, the reaction is much slower as you get further away from the interface. We can also look at the current being driven on the iron. Notice this current is all negative, so this is ORR current. And you see the same thing. When you have the high concentration electrolyte, it's more conductive. You get more ORR current far away from the interface, whereas if you're in the low conductivity electrolyte, it all occurs right at the interface. Now we can also look at the rate of dissolution. This is kind of interesting. So if you look at the rate of dissolution of these two metals uncoupled, for example, a piece of zinc and a piece of iron, you'll find that the rate of zinc dissolution uncoupled is actually very small. And that's because zinc will typically passivate, and iron will dissolve at this rate. Now, when we couple them in the high conductivity electrolyte, what you find is you dramatically lower the dissolution rate of the iron, while dramatically increasing the dissolution rate of the zinc. So why is this? Well, what we've done is we've allowed the cathodic reaction to happen on the zinc, and the corrosion potential, the zinc has moved the corrosion potential down. So if you think about a Evans diagram, that corrosion potential given by the intersection of these lines, zinc is a very active metal. So it's holding the electrochemical potential of electrons quite negative compared to where the iron would be if it was uncoupled. So it suppresses the dissolution of iron at the expense of dissolving zinc. And this is actually called a sacrificial anode. What's interesting though is if you go to lower conductivity electrolytes, what you find is that the zinc dissolves slower and the iron dissolves faster. And the reason is because now we're spending more free energy pushing current through the electrolyte. The corrosion potential is less negative. So the zinc is not able to keep the corrosion potential as negative. That means that the iron oxidation reaction is non-zero at that more anodic corrosion potential, more positive corrosion potential in the lower conductivity electrolyte. So this tells you that sacrificial anodes work best in high conductivity electrolyte, where you can keep the corrosion potential very, very negative, where the less active metal doesn't corrode at all. There's another type of protection called anodic protection, and that's applicable to metals with an active to passive transition. So things like iron, nickel, chromium, titanium. If you apply a large voltage, you can go from a regime, here's where we're going to start, okay, whatever potential this is, and maybe this is the ORR reaction. So if this system was just sitting there, it would go to this corrosion potential. And under these conditions, there's active dissolution going on. So you're going to have some active corrosion, and your part is going to disappear with time. Now, if you could somehow apply a more positive potential, for example, with a potentiostat or a small battery, to raise the potential from the corrosion potential by applying a potential into the passive regime, for example, by growing an oxide layer, a thick oxide layer on iron, nickel, chromium, titanium, even aluminum, you get a thick oxide layer that prevents the oxygen from actually getting in to cause the corrosion. It prevents any electrical current from passing. And now you can passivate and keep a high quality passive layer that protects your metal. So this is called anodic passivation. You might think about this and how it works. Some of the disadvantages are you need an auxiliary electrode because you have your workpiece, you're protecting your metal, and then you got to have somewhere over here some sort of counter electrode, and there's got to be some small amount of current flowing. As I positively charge this thing, there's going to be some small amount of current flowing through the external circuit, and so you're going to have to drive some reaction here, some cathodic reaction here, right, to balance that current. And that uses power, and of course the current always flows in a circle between the metal you're protecting and some counter electrode. Another way to get anodic protection is to change the cathodic reaction so that the cathodic curve intersects the anodic curve in a passive region. So the most common cathodic reaction is the oxygen reduction reaction, but it's pretty slow. And the exchange current density is often proportional to the O2 concentration. So it may be counterintuitive, but one example is you could increase the O2 concentration to shift the cathodic curve up, going from A to B, increasing the rate of mass transport, catalyzing the oxygen reduction reaction. And then the corrosion curves intersect here at this higher potential where the system, the metal, is passivated with an oxide layer. So this is counterintuitive, but by actually providing more oxidizing power chemically, you can also prevent corrosion from happening due to the formation of these passivated layers. Similarly, you can do cathodic protection. You can lower the potential of the metal you want to protect to reduce corrosion. And you can do this either using a sacrificial anode, like we mentioned, or using an external power supply to apply a cathodic current to the metal you want to protect. So imagine here, without protection, the system has V corrosion here and I corrosion here. So here's the cathodic branch of our Evans diagram. Here's the metal dissolution branch. And I don't want the thing to corrode this fast. This is an important piece, maybe a part of my boat, and I want to protect it. So imagine now I have just simply held the voltage of my boat at a lower potential. For example, here, by applying a potential. Then I'd now lower substantially the corrosion potential. If I apply an even more negative potential, I'll actually go on the other side of the metal dissolution curve. So this would actually be spontaneously depositing any metal species. But that again takes power from my external power supply. Now, if you lower the potential too much, you'll have cathodic side reactions, and those can become significant. For example, hydrogen evolution. And this can lead to hydrogen embrittlement, so H can go to grain boundaries, can lead to failure of submetals, which is a problem. Finally, I want to go back to sacrificial anodes. And the idea here is you couple a more active metal like zinc with your metal you want to protect, like iron. And here's the hull of a submarine where these are done. The active metal corrodes to protect the desired metal. The resistance in the metal is much smaller than the solution. So the area protected is a function of the electrical conductivity of the solution. More conductive, more areas protected. This is exactly what we showed on one of the previous slides. Zinc, aluminum, magnesium are often used as sacrificial anodes. Protection is not uniform. You need to sort of optimize the placement of your sacrificial anodes. And it's often determined empirically. But quite simply, this can be understood as follows. The zinc, in this case, will corrode to make zinc 2+. The iron is painted, so there's not very much iron exposed, but if there's any pinholes in the iron, those pinholes is where O2 will attack, and instead of oxidizing the iron will be at a mixed potential controlled by that zinc, and the iron will reduce the oxygen, and it will get its electrons from the corroding zinc instead of from corroding iron. So the zinc is sacrificially dissolving to prevent the iron from dissolving. And this is something that was discovered long ago. There's other types of corrosion protection, for example, in pressed current, cathodic protection. This can be done even in the ground. You use an external electrode, very large electrode here. This is gravel on top of a large anode. You have a DC power supply, for example, attached to your tank. The ground is an electrolyte, it has some salt and water in it. And you drive an anodic reaction, either making oxygen or making Cl2 over here, and that drives a cathodic reaction on the tank. And for an anode, you can use consumables like scrap iron, the anode, or graphite, or inert lead alloys, or platinized metals, or mixed oxide, pretty much anything that can drive a reliable anodic reaction so that you can drive cathodic current through your tank, keep it at a negative potential so it doesn't rust. Here's a ship which has local anodes and a DC power supply to prevent the corrosion of the metal. And of course, when you're driving current, you're driving electrical current through the water. Right? You're driving electrical current through the water, and you're driving some cathodic reaction here, and locally an anode reaction here, and that's preventing your ship from rusting. Now imagine you go up to a metal pier. Now, instead of that current going purely through the electrolyte, because metal's so conductive, the current will actually flow through the pier itself, driving, again, a reduction reaction here and an oxidation reaction here. And so what will happen is actually a ship who has a system on it to protect it from corrosion can actually drive corrosion in the metal pier, which is, I thought, very interesting by forcing current through the metal of the pier based on a cathodic protection system. So that's all I have for you today, and I look forward to talking to you about some of this stuff in class.